All right, guys, so in this video, we are going to start to talk about how to graph polynomials. But before we get into how to graph them by hand, we're first going to talk just a little bit about kind of the way the graphs work and how to read the graphs, as well as what they look like. At this point, we've already talked about solving, so graphing is kind of the next logical thing for us to discuss. Now, most of what we're going to talk about in this section is just review, but it is good stuff to refresh your memory on, especially since it's been since Unit 1 that we've really talked about a lot of this stuff. So that being said, just as a warm-up, I've already written these definitions in, so you might want to pause the video right now to write them down, and I'm going to kind of discuss them in the meantime. So remember that a relative maximum is any point where the function switches from increasing to decreasing. These are the ones that look like the top of a hill when we talk about our graph. A relative minimum is the opposite. So a relative minimum is a point where the function switches from decreasing to increasing. So these look like the bottom of a hill when we look at them on a graph. Remember, the y-intercept is the point where a function crosses the y-axis. The x value for a y-intercept is always 0. And then the x-intercept is the inverse of that, so it is any point where the function crosses the x-axis, and for x-intercepts, the y value is always going to be 0. Now, for increasing and decreasing intervals, remember that we always read a graph from left to right, which means that as x increases, so going from left to right, that when the y values increase, so our graph goes up, that's an increasing interval, and then the inverse of that for the decreasing intervals are where x values increase, so again, still reading the graph from left to right, but now the y values are going down and decreasing. That would be a decreasing interval. So we're going to look at a couple graphs to kind of pull that information from the graph, and then we'll take a look at some with our graphing calculator and kind of work on that. So for each of these two graphs below, we're going to go ahead and find the relative min and max. When I say min and max, I mean relative min and max, as well as the domain and range, and then we'll talk about where the function is increasing, decreasing, and what its end behavior is. So let's take a look at example 1. So we've got our graph. It tells us that the function is negative 2x squared plus 3x. I'm going to go ahead and label a couple of key points for us. It looks like we've got a point right here at 0, 0, and then we've got a second point right here at 1, 1. So first thing, for relative min, that's going to be any point that looks like the bottom of a hill. In this case, that's going to be our point 0, 0. For relative max, we do have one of those as well. Those are going to look like the top of a hill. There's one point on the graph that switches from increasing to decreasing, and that is the point at 1, 1. Now, for domain and range, domain should be easy for all of these. In fact, the domain is always going to be all real numbers. And so that should be kind of an easy point if this were ever asked on a quiz or a test. But for all polynomials, your domain is going to be all real numbers. It turns out that the range is actually the exact same for this first example, because if you notice, on the right side, our graph goes down forever. On the left side, it goes up forever. So we are going from negative to positive infinity. In other words, our graph does in fact cover all real numbers. All right. As for our increasing and decreasing intervals, let's talk about increasing first. There's only one interval where our graph is increasing, that is in between our relative min and max. The x values for that interval are 0 and 1, so we'll say that we are increasing from 0 up to 1, and the way we write that is as 0 less than x less than 1. Remember that for increasing and decreasing, these are only the x values that we are concerned with. So if you want to make a note to yourself, only the x values get used to talk about increasing and decreasing. So that leaves us with two other intervals that must be decreasing. Let's first talk about this one on the left side of our graph. So notice that you are in fact decreasing up until you get to that point at 0, 0. So that would be everything to the left of 0, so where x is less than 0. You are also decreasing everywhere to the right of positive 1. So that would be decreasing also where x is greater or to the right of 1. All right. One last thing to describe, and that's the end behavior for our graph. So that's looking at just what is happening on the ends of our graph. Again, remember, you're not really focused on anything in the middle of the graph. So let's talk about the left side of our graph first. To say the left side, we're going to say that as x approaches negative infinity, so again, as you go to the left side of your graph, then our y values are going up. So as x goes to negative infinity, y goes to positive infinity. For the right side of our graph, we're going to say that as x goes to positive infinity, so that's the way we'll say to the right, our y values this time are going down, so y values are going to negative infinity. All right. So let's take a look at another example of this. Let's go ahead and take a look at number 2. Once again, let me go ahead and label some key points for us here as far as relative minimums and maximums. So we're going to label this point as the point -1, -2. We've got a y-intercept, it looks like, at 0, -3. We've got a point down here, which looks like it's at about 1 and negative, we'll call that 4.5. And then we've got a point here at 2, -1. Now again, these are just approximations. It did say to be sure all answers are exact. I'm going to go ahead and just use some approximations and some holdups to make it a little bit easier. I believe in the homework, your options will be in terms of decimals, so you'll just have to pick whichever decimals are closest to the values that it looks like on the graph. I guess the other thing you could do, if you wanted to actually know, is you could also use your function. Type this function into either Desmos or your graphing calculator, and then you could get the exact values. But for the sake of time in this video, I'm just going to use the rounded numbers. Okay, so as far as relative minimums go, there was one point that looked like the bottom of a hill. That was the point at 1, -4.5, where our graph switched from decreasing to increasing. As for relative max, there's actually going to be 2 of those. There are 2 points where our graph switches from increasing to decreasing, and those are the points -1, -2, and 2, -1. Once again, just like on the previous example, and like I mentioned, all polynomial functions are going to have a domain which is all real numbers, but that's not true of our range on this second example. Notice that our graph does go down towards negative infinity, but then there is a highest point that we can reach, and that highest point is a y value of -1. And so everything less than -1 would work, so that what we'll say for our range is that where y is less than or equal to -1 would be our range for this function. All right, so now for our increasing intervals, there's actually going to be 2 of those increasing intervals. Again, make sure you're reading your graph from left to right. The first one is going to be right here, which is everything to the left of -1. So we'll say where x is less than -1 is one of our increasing intervals. The other increasing interval happens right here. That's from an x value of 1 up to an x value of 2. So we'll say that that's where 1 is less than x is less than 2. There are also 2 decreasing intervals. So our first decreasing interval happens between the x value of -1 and the x value of +1. So that'll be where -1 is less than x is less than 1. The other decreasing interval is everything to the right of +2. So we'll say that that is where x is greater than 2. As for our in behavior, notice that in both directions, our graph is pointed down. So when we're describing our in behavior, let's talk about the left side first. So to say the left side, we'll say that as x goes to negative infinity, our graph is going down, so our y values are also going towards negative infinity. Next, we'll talk about the right side of our graph. So the right side is as x goes to positive infinity, our y values are still going down towards negative infinity. So we'll say that y goes to negative infinity then. Now, on the homework on big ideas, they might have those switched around. So they might tell you what the y values do first and what the x values do second. And if that's the case, then just swap these around and you should be able to find those answers without any trouble. All right. So now that's kind of just a refresher. Again, that's all stuff that's reviewed from Unit 1, where we looked at graphs and read our graphs to figure out some key information. Let's go ahead and practice graphing a little bit. So make sure and grab your graphing calculator, or make sure that you've opened Desmos. I'm going to go ahead and use Desmos today, but if you'd like to use your graphing calculator, you can do that as well. So for each of these polynomial functions, we're going to graph them using a graphing calculator, finding the relative maximums, relative minimums, and x and y intercepts, and then we'll give a simple sketch where we label all of our points. Okay, so for our first one, we've got x cubed plus 2x squared minus 4x minus 8. As we graph that function, here's what that looks like. Let's go ahead and identify some key information. It wanted relative maximums as well as relative minimums, and then it wants our x and y intercepts. Okay, so let's start with relative maximum. It looks like we had one of those at -2, 0. So go ahead and put that point in first. We also had a relative minimum, which had some decimals there at 0.6 repeating, so 2/3, and -9.481. I'll go ahead and just round to the nearest tenth, so that's going to be 0.7 and -9.5. All right. For x-intercepts, there were two x-intercepts actually. There was -2, 0 and 2, 0. For y-intercept, if you go back and look at your graph, we had a y-intercept at 0, -8. Remember that x-intercepts are also the solutions for your graph. In fact, if you go back and take a look, we actually solved this equation in a previous section of the notes. I believe this was actually from the most recent section where we solved this and found out that -2 had a multiplicity of 2, and 2 was just a single solution. So if you want to go back and look, we've already solved it, and those x-intercepts coincide with that. Also, something to point out real quick, notice that the y-intercept is the same as your constant. So just like with quadratics in standard form, when you have polynomials in standard form, that's still going to be the case, because notice if you put 0 in for x, that basically makes everything here 0. And again, your y-intercept ends up being at that value for the constant. Okay, so let's go ahead and graph it. I'm going to go ahead and use this graph to label it. So I'm not going to actually write the points there, but we'll make sure that our first point is at -2, 0. We had another solution or x-intercept at +2, 0. Our y-intercept was at 0, -8. So that would be right here. And then our relative minimum was at 0.7 and -9.5. So that's going to be about right here. So then to create our graph, we're just going to do our best to sketch this. So you're coming up, touching at that x-intercept, coming back down, and then back up. Again, probably not going to be perfect, but it'll get better with practice. All right, let's go and do another example. So we've got f of x equals x cubed minus 6x squared plus 7x plus 2. I've gone ahead and typed that into Desmos for us. Here's what that looks like. Let's go ahead and identify that key information for this graph as well. So go through and tap on each of the values, and then we'll start by listing off the relative maximum. Again, I'm going to go to the nearest tenth, so that's going to be 0.7 and 4.3. Next, we'll go ahead and do our relative minimum. So relative minimum is, let's see, relative minimum was at 3.3 and -4.3, so we'll list that next. For x-intercepts, I believe there were 3 of those. There was -0.2, +2, and then +4.2. So again, that was at -0.2, 0, another one at 2, 0, and the last was at 4.2, 0. For y-intercept, I don't even need to go back to the graph. Remember that that has to be the same as the value for your constant, so that would have to be 0, 2. All right, so as we graph this, we're just going to do our best to get these as close to those decimals as possible. So for the first one, 0.7 and 4.3 is going to be about right in here. For the next one, 3.3 and negative 4.3 is going to be about right in here. For our x-intercepts, we've got negative 0.2 comma 0, so that's just a little bit past negative, or past 0. We've got positive 2 comma 0, and then we've got 4.2 comma 0, and then our y-intercept is at 0 comma 2. So again, your graph isn't going to be perfect, but we'll go ahead and give a sketch here. It looks pretty close to what we saw on Desmos. Okay. Let's go ahead and do 2 more examples, and then we'll talk about one other idea, just an observation that will help you with some of the homework problems, and that'll be it for this video. All right, so the next one, we've got x cubed plus 3x squared minus 4. So we've got that in Desmos here for us. Let's go ahead and identify some of that key information. These all end up being some pretty nice numbers. So we've got negative 2, 0, 0, negative 4, and 1 comma 0, which are going to be the values that we'll use. Obviously, let's talk relative max first. So that's that point, negative 2 comma 0. That's also going to be one of our x-intercepts. For the relative minimum, if you go back and look at your graph, that was at 0, negative 4. That also ends up being your y-intercept as well. Really, the only other point on the graph that we have not used yet is our other x-intercept, which was the point 1 comma 0. All right, so we can be pretty accurate with our labels on this graph and with our points. So we have negative 2 comma 0, 0, negative 4, and then positive 1 comma 0. And we'll just do our best to sketch our graph to make it look like it did on Desmos, something kind of like this. All right, one last example, and this is an example where if you're using your graphing calculator, so your TI graphing calculator, so your 83 or 84, you're going to have to do a little bit of work to find a window that works well for this next function. But Desmos does make it a little bit easier because you can pinch zoom like you're used to. Obviously, you can see that right now it does not look the greatest. In fact, it does go up fairly high on our graph. So we'll have to be kind of careful with our labels for this one. So here are our values for our x-intercepts. Those are actually somewhat nice values. Let me go ahead and get those labeled here for us. So we've got our first is at 0.3 comma 0, negative 0.5, and then negative 3. And then we've got these values as well. Okay. So because our graph goes up to 48.15, I'm going to make my graph go up to 50, and that's going to go up and down by 50. So I'm going to be counting by 5s as I graph this in the notes. So if you want to make sure that your graph is labeled in the same way, that might be helpful. So for the maximum, we've got negative 2.1 comma 48.2. So again, that's negative 2.1 and positive 48.2. For our relative minimum, our point down there at the bottom, negative 0.1 and negative 6.3. So again, negative 0.1 and negative 6.3. For a y-intercept, let's go ahead and just write what that was. So based on our function, we can say that that's at 0 comma negative 6. And now I believe we just have our x-intercepts left to be labeled. So we've got negative 3 comma 0, negative 1/2 comma 0. Let's go ahead and write those first. So negative 3, 0, negative 1/2 comma 0. And then the last one was a decimal. It's 0.3 to the nearest 10th comma 0. All right. Now, remember, as we're labeling our graph, we're counting by 5s. So for our first point, for our maximum, negative 2 comma 48.2 is going to be somewhere kind of right here. For our relative minimum, negative 0.1 and negative 6.3 is going to be somewhere kind of right in here. For our y-intercept, 0 comma negative 6 is going to be very close to that. In fact, those can almost be right next to each other. Then we also have a point at negative 0.5 comma 0. a point at 0.3 comma 0, and one last point at negative 3 comma 0. So again, very, very close in there. Going to be very hard to kind of make this one look good, but our graph came up, came down very quickly through these points, and then back up. All right. So just a quick observation from our notes today, and you might not have picked this up yet. In fact, we'll talk a lot more about this in graphing parts 1 and 2, but this is going to be something that'll show up on the homework a little bit, which is that the minimum degree of a function is always going to be, at minimum, the number of turning points plus 1. So again, just a observation. Which is that our degree of our function, the minimum degree of our function, is the number of turning points plus 1. What I mean by turning points, we'll define that actually in the next section, but the turning points of a graph are the relative maxes and mins. In other words, a graph such as this one has 1, 2 turning points because it has 1 max and 1 min. So our minimum degree for this graph, and we actually know what the degree is, but the minimum degree would be equal to 2 plus 1, which is 3. And so that's going to be at least something that'll be asked a little bit on the homework. I wanted to make sure you guys were prepared for that. That being said, until next time, have a good rest of your day.